In this video, we'll be talking about 3.4 optimization. We'll just start with number 13 here. And number 13 says that a storage box with a square base must have a volume of 80 cubic centimeters. The top and bottom cost 20 cents per square centimeter, and the sides cost 10 cents per square centimeter. Find the dimensions that will minimize cost. I'm going to try to draw a picture here to help you see where my formula is coming from. This is supposed to be a square base in 3 dimensions, and I'm going to have some height here to this box. And it's going to here and here and down there. So the square base is going to be x by x, and I'll call the height y, making my volume equal to x squared times y, and that needs to be equal to 80. So y is going to be equal to 80 over x squared. My cost is that I have 2 of my bases that are x by x, and the price per square foot of those is 20 cents per square centimeter. And I have 4 of my sides that are x by y, this kind of a side right here. There's 4 of those, and those cost 10 cents per square centimeter. So altogether, my cost function is 40 cents times x squared plus 40 cents times xy. And I want to eliminate the y to get everything in terms of x. So c of x is equal to 0.40x squared plus 0.40x times, we said y was 80 over x squared, giving us a c of x of 0.40x squared plus 32 over x, 0.40 times 80 is 32. So now we're going to differentiate. C prime of x is 0.80x minus 32 over x squared, and C double prime of x is equal to 0.80 plus 64 over x cubed. Because x is always going to be a positive number, C double prime is going to always be positive, since I'm going to have a positive times a positive, and whatever my critical number is here is going to be on a concave up piece, forcing this to be a minimum cost. So that is what we want. So this critical number, when we set this equal to 0, we have 0.80x cubed minus 32 is equal to 0. How did I get that? I made a common denominator here. And I'm not worried about the x squared being 0 because I don't want x equals 0. That is not a box when I have no base to it. So I'm interested in when I have 0.80x cubed is equal to 32, making 8x cubed equal to 320. X cubed is equal to 40. And we'll just say x is exactly equal to the cube root of 40. And I want to figure out what that is approximately for you, because you need to measure this in something that makes sense to real life people. So that's about 3.42 centimeters. Let's just verify C double prime of 3.42 is 0.80 plus 64 over 3.42 to the third power is about 2.40, which is greater than 0, is all I care about. So C is minimized when x equals cube root of 40, which is approximately 3.42. And if x is exactly cube root of 40, then y is equal to 80 over the cube root of 40. Cube root of 40 is the cube root of 8 times the cube root of 5. The cube root of 8 is 2. 2 goes into there 40 times. It's exactly 40 over the cube root of 5. And I could rationalize that by multiplying by the cube root of 25 over the cube root of 25. And I would get see, was this squared? This was squared. So this is cube root of, let's just call this 40 to the 2/3 power. Multiply that by 40 to the 1/3 power. 40 to the 1/3 power is going to make this 80 times the cube root of 40 over 40. 40 goes into 82 times is 2 times, and let's come back here to cube root of 40. I don't like this. This is cube root of 8 times cube root of 5 is 2 cube root of 5. So this is 2 times 2 cube root of 5 is 4 cube root of 5 exactly. This is approximately, what did I say? 3.42 centimeters. And this is just about double that. That's 6.84 centimeters. So my dimensions are roughly, well, they're exactly 2 cube root of 5 centimeters by 2 cube root of 5 centimeters by 4 cube root of 5 centimeters exactly, which is approximately 3.42 centimeters by 3.42 centimeters. That's my base, by 6.84 centimeters. That's my height. All right, that was number 13 when we were minimizing the cost of that box that was 80 cubic centimeters. And now we're going to go on to problem number 31. Number 31 asks me to minimize cost as well. Number 31 says an industrial tank of the shape described in exercise 30, which is two hemispheres connected by a right circular cylinder. So it looks like a capsule. I don't know why they're not saying capsule shaped, but you have a hemisphere up here, and you have the other hemisphere of this sphere is down here, and you have a right circular cylinder in there, and it looks like a capsule. So you have an industrial tank that's that shape there that has to have a volume that's going to be, so the volume of the sphere made by the two hemispheres is 4/3 pi r cubed, and the volume of the right circular cylinder portion of the tank is pi r squared h, and the problem tells us that the tank has a volume of 4,000 cubic feet. So let's go ahead and solve for h. It's going to be the oddball out here, so we're going to want 4,000 minus 4/3 pi r cubed is equal to pi r squared h. H is equal to 4,000 divided by pi r squared minus 4/3 pi r cubed divided by pi r squared. That's going to leave me with h of r is 4,000 over pi r squared minus 4/3 r. Now we're going to say that the hemispherical ends cost twice as much per square foot of surface area as the lateral sides. That's pretty common that these ends here have to be stronger than the walls all the way around, just physics reasons like that. So that we'll just call the price of the material P for the cheaper material, just a generic P here. So we have the cost of the side of the sphere is twice as expensive. It's 2p times the 4 let's see, I haven't found the equation here yet. Cost of the tank is 2p 4 pi r squared plus p times, and this is surface area is what I'm getting here, 2 pi RH. So you can look up those formulas for the surface area of a sphere and the surface area of a cylinder. Let me show you what I did. Surface area is the derivative here for this piece. So multiply by 3, drop the exponent by 1. That will be the surface area. Over here, it's the derivative with respect to r as well, 2 pi r h. Imagine you take the circumference, you open up the cylinder all the way like this, and the circumference would be the distance all the way around, which is 2 pi r, and the height of that cylinder is h. And so the area of this is 2 pi RH. Put that all together, and this is 2 times the price of the lateral surface area here to get the price for the spherical ends here, the hemisphere ends. The price of the lateral surface area here is what P is. So let's go ahead and replace H and pull all the other variables out as constants. This is 8 times 4 times 2 is 8 pi r squared times P. And then this is going to be plus 2 pi r P times H. We just found was 4,000 over pi r squared minus 4/3 r. So let's go ahead and pull out our greatest common factor right now that I see is 2 pi r p. Actually, let's distribute first before I do that. Sorry, I want to get rid of that denominator. So let's distribute the pi r in here. So that's going to give me, let's see, 8,000 pi r p over pi r squared. I'll just do everything here, 8 pi r squared p over 3. And I'll make this have a denominator of 3 as well, to say C is equal to 24 pi r squared p over 3. Let's get rid of that. Let's get rid of that. Minus 8 pi r squared p over 3 plus 8,000 p over r. I have the wrong numbers in here. No, we're good. So this is C is 16 pi r squared p over 3 plus 8,000 p over r. going to multiply by r over r and 3 over 3. So c is equal to 16 pi r cubed p plus 24,000 p over 3r. And that gives me a derivative c prime. Let's go back to this form right up. Let's see, c was, before I did this, was 16 thirds pi r squared p plus 8,000 p over r, or let's call that r to the negative first. So c prime is, when I take the derivative with respect to r, is going to be 32 thirds pi rp minus 8,000 p r to the negative second. When I find c double prime, that's going to be 32 thirds pi p plus 16,000 p r to the negative third. So that means that no matter what here, and I'll put this over a denominator of 3 r to the third down here so you can see this is going to be 32 r squared pi p plus 16,000 p. P is always a positive number. It's the price. So we have always a positive number plus always a positive number over always a positive number is always greater than 0 for my second derivative, which means that this critical number from c prime is going to have to give me a minimum cost. And I can find that by 32 thirds pi r p minus 8,000 p over r squared is equal to 0. So p doesn't really matter here. I'm solving for where r is the issue. So p's divide out. 32 pi r over 3 is equal to 8,000 over r squared, which turns into 32 pi r cubed is equal to 24,000. And r cubed is going to be 24,000 divided by 32 pi. And I know that you all probably want to approximate this. So then I want to take the cube root of that. And get that r is just about 6.20 feet. If that's the case, then I can come back to my equation for H all the way up here and say H is approximately 4,000 over pi times, we said R was 6.20 squared minus 4/3 times 6.20. Let's let my calculator do that for me. Alpha y equals n over d, 4,000 over pi times 6.20 times 6.20 minus 4/3 times 6.20 is going to be roughly 24.86. This is feet. These are, this was H, and we said that R was about 6.20 feet. Check that. Four 808. This is 204, and then that makes this 808. When I go to 3 decimal places like the book did, I'll just go ahead and change my entries here to reflect that. 204, 204, and 204 there. And I get 24.808. So round to the nearest thousandth, in this case, thousandth of a foot here. So that's it for that problem. We'll move on now to number 37. And this one was the most interesting to me. Hopefully you find it interesting. And it is gardening, farming. So it says that a strawberry farmer will receive $30 per bushel of strawberries during the first week of harvesting. So we're going to have WP points to start off with. Week 1, $30 per bushel. And then second week of harvesting, the value will drop by 80 cents. So that's going to give me 29.20. Now I'm actually not going to think the way that they tell you to do in the book. They tell you to use point slope form. I want to try to go backwards to slope intercept form to say if I picked them right away, immediately at the time they were ripe, since I lost 80 cents here this way, I should gain 80 cents here this way and get $30.80 as my y-intercept. So that should give me a price equation here that P is equal to a negative 0.80 times the number of weeks after the harvest has ripened fully, plus an initial value of 30.80. So, and I'm going to get another equation here that is going to be based off of some other information. The problem, the farmer estimates that there are approximately 120 bushels of strawberries the first week, and that if he waits another week, that it grows at a rate of 4 bushels a week. So we see that he's going to get more crop, but for a little bit less money each time. And again, I'm going to go backwards and say that if I'm going up by 4 here, I'm going to go down by 4 here, 116. So this is, I'll call B my number of bushels, and it's going up by 4 and plus 116. Now my price per bushel times my number of bushels will give me my revenue. So R of W is going to be equal to negative 0.80 W plus 30.80 times 4 W plus 116. If I multiply all that out, R of W is equal to negative 3.2 W squared plus 30.4 W. That is 116 times negative 0.8 plus 30.8 times 4 is 30.4. That's where I got that from. And then 30.8 times 116 is 3572.8. So that means that R prime of W is equal to a negative 6.4 W plus 30.4. And that means our double prime of W is equal to a negative 6.4, always negative. So whatever I get for this 0 here is definitely going to be a maximum revenue. I'm going to set this equal to 0, and that gives me negative 6.4 W is equal to negative 30.4. Negative 30.4 divided by negative 6.4 is W is 4.75. So that tells me that the farmer here, to maximize his profit, should harvest and sell 4.75 weeks after the time that he thinks that is harvest time. You know, that's what time 0 is there's a date that's set on the calendar that typically is you should pick the strawberries this many weeks after you plant them. That's your harvest date. And he says, but if I wait a little bit longer, I might not get the highest cost for the strawberries, but I'll get more strawberries that I can sell at a little bit lower price, and I might make more money in the end. So he should pick 4.75 weeks after that date to maximize his revenue here. And let's see now what that optimal price that he'll get is and the optimal number of bushels that he'll get. So P of 4.75 weeks is negative 0.80 times 4.75 plus 30.80, negative 0.8 times 4.75 plus 30.8 is $27 per bushel. Number of bushels that you'll get after 4.75 weeks is 4 times 4.75 plus 116 will be 135 bushels, making my revenue that I generate at 4.75 weeks, 135 bushels times $27 per bushel. Maximum revenue will be 135 times 27 is $3,645 in revenue for this farmer's crop. So that's it for these examples. There's a couple other suggested problems that I'll leave you to do on your own. I think that was a sufficient sampling of the techniques there for you. And so we'll pick up with 3.5 next time. No, we'll do a couple questions from the quick quiz actually next time that comes at the end of 3.4. So rarely do we do this, but there's a couple more optimization problems that I want to do that are in your quick quiz section, not in your exercises for the section. So I'll come back and do those in a separate video since it's a little extra section tacked on to give you a little extra practice on 3.4. So we'll come back and do that next time. See you for the next video.